In April 2026, on a mountaintop in Arizona, 5,000 fiber-optic eyes turned toward the sky near the Little Dipper. Every 20 minutes, they locked onto new points of light, galaxies and quasars whose photons had traveled for billions of years. By sunrise, DESI had crossed a historic threshold. The Dark Energy Spectroscopic Instrument had completed observations for its originally planned 3D map of the universe, one of the most extensive surveys of the cosmos ever conducted. And it did more than planned. Instead of measuring light from 34 million galaxies and quasars, DESI observed more than 47 million, plus more than 20 million stars, creating the largest high-resolution 3D map of the universe to date. But this is not just a map of space. It is a map through time, a record of where matter gathered, where cosmic voids opened, and how the universe changed as it expanded. Now scientists are asking what this map can reveal about one of the deepest mysteries in physics. Why is the universe expanding faster and faster? That question brings us to dark energy. The universe is expanding faster and faster, widening the nearly empty space between galaxies. We know this is happening, but we do not know why. Scientists use the term dark energy to describe this accelerating expansion. It could be caused by a previously unknown force, or it may mean we need to rethink the laws of gravity on the largest scales. Dark energy is one of the biggest mysteries in modern science. It appears to make up about 68% of the universe, yet we still do not know what it actually is. To understand it, scientists need better measurements of the expansion rate, and how that rate has changed over cosmic time. That means looking far into the universe, where light has been traveling toward Earth for billions of years. The farther away an object is, the farther back in time we see it. So by measuring millions of galaxies and quasars at different distances, scientists can begin to reconstruct the history of cosmic expansion. This is why DESI was built. Not simply to take beautiful pictures of the sky, but to measure the light from millions of objects and turn those measurements into a 3D map of the universe. To do that, DESI had to transform a mountaintop telescope into one of the most precise cosmic mapping machines ever made. DESI is mounted on the Nicholas U. Mayall telescope at Kitt Peak National Observatory near Tucson, Arizona. To build its three-dimensional map, DESI measures light, not from one galaxy at a time, but from thousands of targets in a single exposure. First, light from distant galaxies and quasars reflects off the telescope's 4-meter primary mirror. From there, it passes through a set of large lenses that give DESI a wide, sharply focused view of the sky, covering an area many times larger than the full moon. That wide view is essential. Every clear night, DESI looks at one patch of sky, then another, slowly filling in the survey area with millions of separate measurements. After passing through the lenses, the light reaches DESI's focal plane at the top end of the telescope. This is where the machine becomes extraordinary. Across that focal plane are 5,000 robotic positioners. Each one carries a single optical fiber, and each fiber can be aimed at one selected target: a galaxy, a quasar, or a star. Before each observation, the robots move into place with extreme precision. They form a new pattern that matches the positions of objects in that part of the sky. Then, the telescope gathers the light. Roughly every 20 minutes, DESI can move on to a new set of targets. The robots shift again, the fibers line up again, and another piece of the universe is measured. This automated dance allows DESI to observe thousands of objects at once, night after night, building the survey one field at a time. The optical fibers serve almost like DESI's eyes. They collect light that has traveled across billions of years, then guide it away from the focal plane and down through the telescope. But the power of DESI is not only in the number of objects it can observe. It is in the precision of the machine that makes those observations possible. To understand that precision, we need to look closer at the fiber optic system itself and at the people who built it.
The DESI project is a crazy machine. It's really exciting to work on. It has 5,000 individual fiber positioning robots. Each one moves a single fiber to target a single galaxy at a time. And that allows us to do massively parallel survey of the universe, where we can measure 5,000 galaxies at a time, very precisely measure their light, take spectra, and then move on to the next set of 5,000 every 20 minutes. So it's a rapidly cycling survey. Here we're installing the fiber positioner robots into the petals. There are 10 petals. Each one of them is a 36-degree wedge, and 10 of those form the focal plane of the DESI instrument. Each petal has 500 robots, and each robot has a single 3-meter length of fiber. Those fibers then need to get spliced to a 50-meter cable. Each cable carries 500 fibers, and those ultimately route down off the telescope to the ground floor of the telescope, where they're the spectroscopes that measure the light. The DESI focal plane has over 600,000 different parts in the DESI focal plane, which is only a volume about this big. As I said, it's a crazy, insane instrument that we're putting together.
We've used the fibers because we build the front-end focal plane system in one section, and then we build the fiber cable to the spectrograph assembly in a separate section. And then we have to join those two sections together. The most efficient way to do that is with fusion splicing. So we expose the bare strands of glass, and then we heat them up in a very precise way to make that connection without any losses in terms of optical quality or throughput or any degradation of the light.
It's been amazing, after having done literally years of modeling in the computer, how all these parts were going to fit together and work together, to see us starting to put the real hardware together, and it actually just fits. That's really gratifying.
From DESI's focal plane, the optical fibers carry the captured light down the length of the telescope to 10 spectrographs. This is where the light is separated into a spectrum, a range of colors that contains information about the object it came from. For DESI, that spectrum is the key. As the universe expands, light from distant galaxies is stretched while it travels through space. The farther that light has traveled, the more its wavelengths are shifted toward the red end of the spectrum. This is called redshift. By measuring redshift with extreme precision, DESI can estimate how far away a galaxy or quasar is, and how quickly space has expanded since that light began its journey. One measurement gives scientists one point in the map. Millions of measurements create something far more powerful, a three-dimensional record of the universe across billions of years. DESI does not simply show where galaxies are. It helps reveal how the universe grew, how matter gathered, and how the largest structures in the cosmos formed. And when those measurements are combined, a hidden pattern begins to appear. When DESI's measurements are placed into position, the universe begins to look less like an empty darkness and more like a vast structure. In these maps, galaxies and quasars become points in 3 dimensions. Some gather in long strands and dense clusters. Others outline enormous empty regions, called cosmic voids. Together they form the cosmic web, the largest pattern we can see in the universe. This is where DESI's scale becomes visible. The survey is not only measuring distant objects, it is revealing how matter arranged itself across billions of years, as gravity pulled galaxies together and expansion stretched space between them. The deeper we look into the map, the farther back in time we are seeing. Nearby galaxies show a more recent universe. Distant galaxies and quasars show the universe as it was billions of years ago. So DESI's map is not flat, it is a timeline. It lets scientists compare the young universe with the more recent universe and ask how fast space was expanding at different times. But hidden inside this cosmic web is something even more useful, a faint ancient pattern that works like a ruler. Inside the cosmic web, scientists look for a pattern left over from the universe's earliest moments. Long before stars and galaxies existed, the young universe was hot, dense, and filled with matter and light. Tiny pressure waves moved through that early plasma, spreading outward like ripples in a pond. As the universe expanded and cooled, those waves stopped moving. But the pattern they created did not disappear. It became frozen into the way matter would later gather, leaving a faint, repeated spacing in the positions of galaxies. This pattern is called baryon acoustic oscillations, or BAO. For DESI, BAO acts like a cosmic ruler. By measuring the apparent size of this ancient pattern at different distances, scientists can estimate how far away those galaxies are and how much the universe has expanded since their light began traveling toward us. Nearby galaxies show the ruler in the more recent universe. Distant galaxies and quasars show the ruler billions of years in the past. That is how DESI turns a map of galaxies into a history of expansion. The map is not only showing where objects are, it is measuring how space itself changed over time. And when scientists compare those measurements with the standard model of the universe, they find something intriguing, a possible hint that dark energy may not be as constant as once thought. For years, the simplest explanation for dark energy has been that it is constant, a steady property of space itself. In the standard model of cosmology, dark energy helps drive the accelerating expansion of the universe, while matter and dark matter slow that expansion through gravity. DESI was built to test that balance with new precision, and its early results have made the story more interesting. When scientists compared DESI's measurements with other cosmological data, they found hints that dark energy may not be perfectly constant. It may have changed over time. That does not mean the mystery is solved. A hint is not a discovery. It could grow stronger with more data. It could also fade as measurements improve. But if dark energy is changing, it would mean our current picture of the universe is incomplete, and the future of cosmic expansion may be different from what scientists once expected. That is why DESI's completed map matters so much. The instrument has now gathered the full planned survey dataset, giving researchers their best chance yet to test whether this hint is real. The original DESI survey is now complete, but the story is not over. After beginning science observations in May 2021, DESI finished the observations for its planned 5-year map ahead of schedule, with far more data than expected. The goal was to measure light from 34 million galaxies and quasars. Instead, DESI observed more than 47 million galaxies and quasars, along with more than 20 million stars in our own Milky Way. That completed map now gives scientists an enormous new dataset to process. The first dark energy results from the full 5-year survey are expected in 2027, and DESI is still observing. Through 2028, the project is set to expand its map from about 14,000 square degrees of sky to about 17,000. It will also revisit parts of the original survey area, collecting data from fainter and more distant galaxies to make the map denser and more detailed. Beyond dark energy, the same instrument can help scientists study dwarf galaxies, stellar streams, and the hidden dark matter shaping the Milky Way. So DESI has reached a milestone, but not an ending. The map is complete enough to change what scientists can ask, and still unfinished enough to keep surprising us. Before we leave this story, there is one final thing to remember. DESI reminds us that the universe is not only enormous, it is still becoming something. Dark energy may be invisible, but its effects are written across the sky, in the motion of galaxies, in the shape of the cosmic web, and in light that has traveled billions of years to reach us. And maybe that is the most inspiring part. Even when the universe gives us a mystery this big, we keep building better tools, asking better questions, and looking a little deeper. So thank you for watching. If you enjoyed this journey through DESI's map of the cosmos, please give the video a thumbs up, subscribe, and join us for the next trip into the unknown. Because apparently, even the universe likes to keep its secrets in 3D. And as we always say here on Wormhole to Cosmos, remember, the universe is vast, mysterious, and full of wonders waiting to be explored. Stay curious, keep looking up, and until next time, keep your eyes on the stars.